Okay, let's dive into this. Welcome to this explainer. Today, we're laser focused on one primary goal, making absolutely sure you aced your manufacturing lab evaluation and that practical exam. We've got a ton of ground to cover, from the actual sparks flying in the welding bay to the high-tech precision of computer numerical control. But I promise you, by the end of our time together today, you are going to feel completely prepared to crush it.
Here's our roadmap. We'll be doing a rapid tour through conventional machining, welding, and 3D printing. And then, we are hitting the brakes for a serious deep dive masterclass on the CNC lathe fundamentals and the exact practical procedure you'll need.
All right, kicking things off with Section 1, Conventional Machining and Forming. Stay sharp. We're going to rapid fire through these manual stations.
So, comparing the conventional lathe and the milling machine, both of these rely on high-speed steel, or HSS, single-point cutting tools to work on mild steel. But listen closely, because this is a strict, non-negotiable safety rule for your practical. Your chucks absolutely must be meticulously centered. If you're handed a 3-spoke chuck, you're in luck. It auto-centers. But if you get a 4-spoke chuck, you have to manually center it using chalk to mark the high spots. Literally, do not skip that step.
Now, moving over to sheet metal, you'll be working with a massive 72-inch bed for manual bending. The goal here is usually hitting a precise 45-degree angle to create a solid seam. But I gotta drop a crucial real-world safety note directly from the lab manual here. The metal they give you for this task is highly septic. Seriously, if you slip and get a cut, no matter how small, do not put your finger in your mouth. Go wash it immediately. Precision is great, but safety is always number one.
Let's keep the energy up as we pivot into Section 2, Welding Processes and Foundry.
Over in the welding bay, you really need to know the distinctions between your three main processes. MMA, or manual metal arc, relies on high current and low voltage to melt a flex-coated rod. Then you have MIG, metal inert gas, which is semi-automatic and uses a shielding gas mix of argon and CO2. It's cheap and perfect for mild steel. Finally, resistant spot welding uses highly conductive copper electrodes to literally pinch and fuse the metal together. Oh, and before I forget, here's an explicit warning for MMA. Never place the electrode holder on the table. Rest it on the shield and only on the shield.
Okay, what's really interesting here is that these next definitions are guaranteed Viva questions. Let's lock them in so you can recite them in your sleep. Autogenous welding. That joins similar metals with absolutely zero filler. Homogeneous joins similar metals but brings a filler metal into the mix. And heterogeneous joins completely dissimilar metals using a filler. Commit those three to memory and you'll bag those exam points easy.
Down in the foundry, your sand casting procedure follows a very strict sequence. You start by filling the drag, that's the bottom box, with green sand, packing it incredibly tight with a wedge rammer. Quick pro tip, green sand needs exactly 7% moisture to hold its shape. If it's right, it packs together just like a perfect snowball. Next, insert your pattern, place the cope on top, poke your vent holes so the gas can escape, and pour your molten aluminum at exactly 660 degrees Celsius.
Moving into the digital era of the lab now, with Section 3, Additive and CNC Milling.
For the FDM 3D printer, you gotta know your filament specs. ABS needs serious heat, like 230 to 250 degrees Celsius, and it demands a fully closed printing environment. If it cools too fast, it shrinks and cracks, which is a nightmare. PLA, on the other hand, is way more forgiving. It prints beautifully at 195 degrees in an open setup. Also, be smart about supports. Use a brim for flat stuff and a raft to give a solid base for anything tall.
When we bridge that gap from conventional to CNC milling, we're taking a massive technological leap. We are fundamentally trading hand cranks for automated precision. So instead of manually cranking carriage wheels for your X and Y axes, the CNC mill uses an automatic tool changer, or ATC, and runs entirely on coordinate programming. You just tell the machine the coordinates and it executes it flawlessly.
All right, Section 4, CNC Lathe, Essential Fundamentals. So, the crucial point is, this is where we slow down and really get into the masterclass. Let's demystify this heavy alphabet soup right off the bat, so you're speaking the machine's language perfectly before you even touch the panel. MDI is manual data input. That's just how you type in G-code by hand. EOB stands for end of block. Think of it exactly like hitting the Enter key on your laptop. It just confirms that line of code. And as we just mentioned, ATC is your automatic tool changer. Simple, right?
When you walk up to that CNC lathe for the evaluation, here is the baseline setup you're going to face. It's a 2-axis machine, just X and Z. You'll be using a carbide tip cutting tool on an aluminum workpiece. The machine maxes out at 3,000 RPM. And this is the vital part for your manual adjustments. One step on the dial equals 0.1 millimeters, which is exactly 100 microns. Keep that scale in your head.
Now, you absolutely must clarify this mechanical difference in your mind right now. Step mode versus jog mode. In step mode, the tool moves that tiny, microscopic set distance every single time you click the button. It's for extreme, surgical precision. But in jog mode, the tool just moves continuously for as long as you hold the button down. If you mix these two up during the practical, you are going to crash the machine and instantly ruin your workpiece. No pressure, right?
Okay, Section 5, CNC Lathe, Practical Procedure. Lock in with me here because this is the exact step-by-step procedural breakdown you need to memorize.
And this brilliantly illustrates exactly what you'll be staring at during the exam, the CNC 4640 control panel. Notice the cluster of directional arrows, those MPG step controls, and the axis buttons. We're going to walk through exactly how you navigate this board to set up and run your job flawlessly.
Let's start with the boot up sequence. First, obviously, turn the machine on. Second, you have to manually tell the machine to load up your specific tool. You'll punch in M06T101 to grab that single-point cutting tool. Once it's locked in, switch over to jog mode, dial your jog rate way down to a nice safe 10%, and carefully maneuver the tool tip so it's just hovering right near your aluminum stock. Okay, now we establish the Z-axis offset. We're basically telling the brain of the machine where the very front face of the material is. Set your spindle to 1500 RPM. Then, and please remember this, switch your MPG to step mode for safety. Step the tool in until it barely kisses the face of the job and complete a facing pass. Once that's done, you need to save it. Navigate to Coord, then Edit, and input your cut length as exactly 0. Boom, you've just zeroed your Z-axis. Next is the X-axis offset, which tells the machine the exact outer diameter. Go back to jog, get near the outer curve, and turn the spindle on. Switch back to step mode and inch it in until you just barely scratch the spinning diameter. Now turn the spindle off, but do not move the tool's position. Go back into the menu, Coord, then Edit, and input the cut diameter. Since your stock is exactly 1 inch, you are going to type in 25.4 millimeters.
You are basically ready to cut. Move the machine to its home position and hit Start. Do a quick check of your offsets in MDI to make sure no stray random codes are active. Then, pull up the File menu and load Project T3 from the D drive. To actually run the turning program safely, you'll use this exact sequence. Hit Auto, hit Reset, turn on SBK, which stands for Single Block Mode, meaning it reads just one line of code at a time to prevent any disastrous crashes, and finally, hit Start.
And that brings us to the end of the masterclass. But before we wrap, I want to leave you with this provocative little scenario to really test your readiness. If you've just input your X offset as 25.4 millimeters, what is the very next immediate button or sequence you execute before loading that project file? Think carefully about where that tool needs to go first for safety's sake. Really chew on that. Thank you so much for being such focused learners today. Review these steps, visualize that control panel in your mind, and you are undoubtedly going to crush this lab evaluation.